Hello everyone, this is Saurav from Edureka, and today we'll be focusing on recurrent neural networks. So without any further ado, let us move forward and have a look at the agenda for today. So we'll begin by understanding why can't we use feedforward networks for various problems. We'll focus on various issues with feedforward networks. After that, we'll understand how recurrent neural networks solve those issues, and we'll understand how exactly it works. Then we'll focus on various issues with recurrent neural networks, namely vanishing and exploding gradient. After that, we'll understand how LSTMs, that is long short-term memory units, solves this problem. And finally, we'll be looking at an LSTM use case. So guys, let's begin. We'll understand why can't we use feed-forward networks. Now let us take an example of a feed-forward network that is used for image classification. So we have trained this particular network for classifying various images of animals. Now if you feed in an image of a dog, it will identify that image and will provide a relevant label to that particular image. Similarly, if we feed in an image of an elephant, it will provide a relevant label to that particular image as well. Now if you notice, the new output that we have got, that is classifying an elephant, has no relation with the previous output, that is of a dog. Or you can say that the output at time t is independent of output at time t minus 1. As we can see that there is no relation between the new output and the previous output. So we can say that in feed-forward networks, outputs are independent to each other. Now there are a few scenarios where we actually need the previous output to get the new output. Let us discuss one such scenario. Now what happens when you read a book? You'll understand that book only on the understanding of your previous words. Alright, so if I use a feed-forward network and try to predict the next word in a sentence, I can't do that. Why can't I do that? Because my output will actually depend on the previous outputs. But in the feed-forward network, my new output is independent of the previous outputs. That is, output at t plus 1 has no relation with output at t minus 2, t minus 1 and at t. So basically we cannot use feed-forward networks for predicting the next word in a sentence. Similarly, you can think of many other examples where we need the previous output, some information from the previous output, so as to infer the new output. This is just one small example. There are many other examples that you can think of. So we'll move forward and understand how we can solve this particular problem. So over here what we have done, we have input at t minus 1. We'll feed it to our network. Then we'll get the output at t minus 1. Then at the next timestamp, that is at time t, we have input at time t that will be given to our network along with the information from the previous timestamp, that is t minus 1, and that will help us to get the output at t. Similarly, at output for t plus 1, we have two inputs. One is a new input that we give. Another is the information coming from the previous timestamp, that is t, in order to get the output at time t plus 1. Similarly, it can go on. So over here, I have just written a generalized way to represent it. There's a loop where the information from the previous timestamp is flowing. And this is how we can solve this particular challenge. Now let us understand what exactly are recurrent neural networks. So for understanding recurrent neural network, I'll take an analogy. Suppose your gym trainer has made a schedule for you. The exercises are repeated after every third day. Now this is the order of your exercises. First day you'll be doing shoulders, second day you'll be doing biceps, third day you'll be doing cardio. And all these exercises are repeated in a proper order. Now what happens when we use a feed-forward network for predicting the exercise today? So we'll provide in the inputs such as day of the week, month of the year and health status. Alright, and we need to train our model or our network on the exercises that we have done in the past. After that, there'll be a complex voting procedure involved that will predict the exercise for us. And that procedure won't be that accurate. So whatever output we'll get won't be as accurate as we want it to be. Now what if I change my inputs and I make my inputs as what exercise I've done yesterday? So if I've done shoulder, then definitely today I'll be doing biceps. Similarly, if I've done biceps yesterday, today I'll be doing cardio. Similarly, if I've done cardio yesterday, today I'll be doing shoulder. Now there can be one scenario where you are unable to go to gym for one day. Due to some personal reasons, you could not go to the gym. Now what will happen at that time? We'll go one timestamp back and we'll feed in what exercise that happened day before yesterday. So if the exercise that happened day before yesterday was shoulder, then yesterday there were biceps exercises. Alright, similarly biceps happened day before yesterday, then yesterday would have been cardio exercises. Similarly, if cardio would have happened day before yesterday, yesterday would have been shoulder exercises. Alright, and this prediction, the prediction for the exercise that happened yesterday will be fed back to our network, and these predictions will be used as inputs in order to predict what exercise will happen today. Similarly, if you have missed your gym say for 2 days, 3 days or 1 week, so you need to roll back. You need to go to the last day when you went to the gym. You need to figure out what exercise you did on that day, feed that as an input, and then only you'll be getting the relevant output as to what exercise will happen today. Now what I'll do, I'll convert these things into a vector. Now what is a vector? Vector is nothing but a list of numbers. Alright, so this is the new information guys along with the information from the prediction at the previous timestamp. So we need both of these in order to get the prediction at time t. Imagine if I have done shoulder exercises yesterday. So this will be 1, this will be 0, and this will be 0. Now the prediction that will happen will be biceps exercise, because if I have done shoulder yesterday, today it will be biceps. So my output will be 0, 1 and 0. And this is how vectors work guys. So I hope you have understood this guys. Now this is how a neural network looks like guys. We have new information along with the information from the previous timestamp. The output that we have got in the previous timestamp will use certain information from that, will feed into our network as inputs, and then that will help us to get the new output. Similarly, this new output that we have got will take some information from that, feed in as an input to our network along with the new information to get the new prediction, and this process keeps on repeating. Now let me show you the math behind the recurrent neural networks. So this is the structure of a recurrent neural network guys. Let me explain you what happens here. Now consider at time t equals to 0, we have input x0 and we need to figure out what is h0. So according to this equation, h of 0 is equal to wi weight matrix multiplied by our input x of 0 plus wr into h of 0 minus 1, which is h of minus 1, and time can never be negative, so this particular equation cannot be applied here, plus a bias. So wi into x of 0 plus bh passes through a function g of h to get h of 0 over here. After that I want to calculate y0. So for y0 I'll multiply h of 0 with the weight matrix wi and I'll add a bias to it and pass it through a function g of y to get y0. Now in the next timestamp, that is at time t equals to 1, things become a bit tricky. Now let me explain you what happens here. So at time t equals to 1 I have input x1. I need to figure out what is h1. So for that I'll use this equation. So I'll multiply wi, that is the weight matrix, by the input x1 plus wr into h of 1 minus 1, which is 0. H of 0 we know what we got from here. So wr into h of 0 plus the bias, pass it through a function g of h to get the output as h1. Now this h1 will use to get y1. We'll multiply h1 with wi plus a bias and we'll pass it through a function g of y to get y1. Similarly, in the next timestamp, that is at time t equals to 2, we have input x2. We need to figure out what will be h2. So we'll multiply the weight matrix wi with x of 2 plus wr into h of 1 that we have got here plus b of h and pass it through a function g of h to get h of 2. From h of 2, we'll calculate y of 2, wi into h of 2 plus by, that is the bias, pass it through a function g of y to get y2. And this is how recurrent neural network works, guys. Now you must be thinking how to train a recurrent neural network. So a recurrent neural network uses backpropagation algorithm for training. But backpropagation happens for every timestamp. That is why it is commonly called as backpropagation through time. Now with backpropagation there are certain issues, namely vanishing and exploding gradients. Let us see those one by one. So in vanishing gradient what happens? When you use backpropagation, you tend to calculate the error, which is nothing but the actual output that you already know minus the model output, the output that you got through your model, and the square of that. So you figure out the error. With that error, what do? You tend to find out the change in error with respect to change in weight or any variable. So we'll call it weight here. So change of error with respect to weight multiplied by learning rate will give you the change in weight. Then you need to add that change in weight to the old weight to get the new weight. Alright. So obviously what we are trying to do, we are trying to reduce the error. So for that we need to figure out what will be the change in error if my variables are changed, right? So that way we can get the change in the variable and add it to our old variable to get the new variable. Now over here what can happen if the value dE by dW, that is a gradient, or you can say the rate of change of error with respect to our variable weight, becomes very small than 1, like it is 0.00 something. So if you multiply that with the learning rate, which is definitely smaller than 1, then you get the change of weight which is negligible. Alright, so there might be certain examples where you are trying to predict, say, a next word in a sentence and that sentence is pretty long. For example, if I say I went to France dash dash dash, I went to France, then there are certain words, then I say few of them speak dash. Now I need to predict speak, what will come after speak. So for that I need to go back in time and check what was the context, which will be very complex, and due to that there will be a lot of iterations, and because of that this error, this change in weight will become very small, very small. So the new weight that we'll get will be actually almost equal to your old weight. So there won't be any updation of weight that will be happening. And that is nothing but your vanishing gradient. Alright, I'll repeat it once more. So what happens in backpropagation, you first calculate the error. This error is nothing but the difference between the actual output and the model output and the square of that. With that error, we figure out what will be the change in error when we change a particular variable, say weight. So dE by dW, multiply it with learning rate to get the change in the variable or change in the weight. Now we'll add that change in the weight to our old weight to get the new weight. This is what backpropagation is, guys. Alright, I'm just giving you a small introduction to backpropagation. Now consider a scenario where you need to predict the next word in a sentence. And your sentence is something like this. I have been to France. Then there are a lot of words. After that, few people speak. And then you need to predict what comes after speak. Now if I need to do that, I need to go back and understand the context. What is it talking about? And that is nothing but your long-term dependencies. So what happens during long-term dependencies, if this dE by dW becomes very small, then when you multiply it with n, which is again smaller than 1, you get delta W, which will be very, very small. That will be negligible. So the new weight that you'll get here will be almost equal to your old weight. So I hope you're getting my point. So this new weight, so there will be no updation of weights, guys. This new weight will definitely will always be almost equal to our old weight. So there won't be any learning here. So that is nothing but your vanishing gradient problem. Similarly, when I talk about exploding gradient, it is just the opposite of vanishing gradient. So what happens when your gradient or dE by dW becomes very large, becomes greater than 1, all right? And you have some long-term dependencies. So at that time, your dE by dW will keep on increasing, delta W will become large, and because of that, your weights, the new weight that will come will be very different from your old weight. So these two are the problems with backpropagation. Now let us see how to solve these problems. Now exploding gradients can be solved with the help of truncated BTD, backpropagation through time. So instead of starting backpropagation at the last timestamp, we can choose a smaller timestamp like 10. Or we can clip the gradients at a threshold. So there can be a threshold value where we can, clip the gradients. And we can adjust the learning rate as well. Now for vanishing gradient, we can use a ReLU activation function. We have discussed ReLU activation function in artificial neural network tutorial, guys. Similarly, we can also use LSTM and GRUs. In this tutorial, we'll be discussing LSTMs, that are long short-term memory units. Now let us understand what exactly are LSTMs. So guys, we saw what are the two limitations with the recurrent neural networks. Now we'll understand how we can solve that with the help of LSTMs. Now what are LSTMs? Long short-term memory networks, usually called as LSTMs, are nothing but a special kind of recurrent neural network. And these recurrent neural networks are capable of learning long-term dependencies. Now what are long-term dependencies? I've discussed that in the previous slide, but I'll just explain it to you here as well. Now what happens, sometimes we only need to look at the recent information to perform the present task. Now let me give you an example. Consider a language model trying to predict the next word based on the previous ones. If we are trying to predict the last word in the sentence, say the clouds are in the sky. So we don't need any further context. It's pretty obvious that the next word is going to be sky. Now in such cases where the gap between the relevant information and the place that it's needed is small, RNNs can learn to use the past information. And at that time, there won't be such problems like vanishing and exploding gradient. But there are few cases where we need more context. Consider trying to predict the last word in the text, I grew up in France. Then there are some words. After that comes, I speak fluent French. Now recent information suggests that the next word is probably the name of a language. But if we want to narrow down which language, we need the context of France from further back. And it's entirely possible for the gap between the relevant information and the point where it is needed to become very large. And this is nothing but long-term dependencies. And the LSTMs are capable of handling such long-term dependencies. Now LSTMs also have a chain-like structure like recurrent neural networks. Now all the recurrent neural networks have the form of a chain of repeating modules of neural networks. Now in standard RNNs, the repeating module will have a very simple structure such as a single 𝐾 layer that you can see. Now this 𝐾 layer is nothing but a squashing function. Now what I mean by squashing function is to convert my values between -1 and 1. Alright, that's why we use 𝐾. And this is an example of an RNN. Now we'll understand what exactly are LSTMs. Now this is a structure of an LSTM. Or if you notice, LSTM also have a chain-like structure, but the repeating module has different structures. Instead of having a single neural network layer, there are 4 interacting in a very special way. Now the key to LSTM is the cell state. Now this particular line that I'm highlighting, this is what is called the cell state. The horizontal line running through the top of the diagram. So this is nothing but your cell state. Now you can consider the cell state as a kind of a conveyor belt. It runs straight down the entire chain with only some minor linear interactions. Now what I'll do, I'll give you a walkthrough of LSTM step by step, alright? So we'll start with the first step. Alright guys, so the first step in our LSTM is to decide what information we are going to throw away from the cell state. And you know what is a cell state, right? I've discussed in the previous slide. Now this decision is made by the sigmoid layer. So the layer that I'm highlighting with my cursor, it is a sigmoid layer called the forget gate layer. It looks at ht-1, that is the information from the previous timestamp, and xt, which is the new input, and outputs a number between 0 and 1 for each number in the cell state ct-1, which is coming from the previous timestamp. A 1 represents completely keep this, while a 0 represents completely get rid of this. Now if we go back to our example of a language model trying to predict the next word based on all the previous ones, in such a problem, the cell state might include the gender of the present subject so that the correct pronouns can be used. When we see a new subject, we want to forget the gender of the old subject, right? We want to use the gender of the new subject. So we'll forget the gender of the previous subject here. This is just an example to explain you what is happening here. Now let me explain you the equations which I've written here. So ft will be combining with the cell state later on, that I'll tell you. So currently ft will be nothing but the weight matrix multiplied by ht-1 and xt and plus the bias, and this equation is passed through a sigmoid layer. Alright, and we get an output that is 0 and 1. 0 means completely get rid of this, and 1 means completely keep this. Alright, so this is what basically is happening in the first step. Now let us see what happens in the next step. So the next step is to decide what information we are going to store. In the previous step, we decided what information we are going to keep, but here we are going to decide what information we are going to store here. Alright, what new information we are going to store in the cell state. Now this has two parts. First, a sigmoid layer, this is called a sigmoid layer, and which is also known as an input gate layer, decide which values we'll update. Alright, so what values we need to update. Then there's also a tan-hash layer that creates a vector of the candidate values c bar of t-1 that will be added to the state later on. Alright, so let me explain it to you in a simpler terms. So whatever input that we are getting from the previous timestamp and the new input, it will be passed through a sigmoid function which will give us I of t. Alright, and this I of t will be multiplied by ct, which is nothing but the input coming from the previous timestamp and the new input with that is passed through a tan-hash, that will result in ct. And this will be later added on to our cell state. And the next step will combine these two to update the states. Now let me explain the equations. So I of t will be what? Weight matrix, and then we have ht-1 comma xt multiplied by the weight matrix plus the bias, pass it through a sigmoid function, we get I of t. C bar of t will get by passing a weight matrix ht-1 xt plus bias through a tan-hash squashing function, and we'll get C bar of t. Alright, so as I've told you earlier as well, in the next step we'll combine these two to update the state. Let us see how we do that. So now is the time to update the old cell state ct-1 with the new cell state ct. Alright, and the previous steps we have already decided what to do. We just need to actually do it. So what we'll do, we'll multiply the old cell state ct-1 with ft that we got in the first step, forgetting the things that we decided to forget earlier in the first step, if you can recall. Then what we do, we add it to it and ct, then we add it by the term that will come after multiplication of it and c bar t, and this new candidate value scaled by how much we decided to update each state value. Alright, so in the case of the language model that we were discussing, this is where we would actually drop the information about the old subject gender and add the new information as we decided in the previous steps. So I hope you are able to follow me, guys. Alright, so let us move forward and we'll see what is the next step. Now our last step is to decide what we are going to output, and this output will depend on our cell state, but it will be a filtered version. Now finally what we need to do is we need to decide what we are going to output, and this output will be based on our cell state. First we need to pass ht-1 and xt through a sigmoid activation function so that we get an output that is OT. Alright, and this OT will be in turn multiplied by the cell state after passing it through a tan-hash squashing function or an activation function. And why we do that? Just to push the values between -1 and 1. So after multiplying OT, that is this value, and a tan-hash CT, we'll get the output H2, which will be a new output, and that will only output the part that we decided to. whatever we have decided in the previous steps, it will only output that value. Alright, now I'll take the example of that language model again. Since it just saw a subject, it might want to output information relevant to a verb, and in case that's what is coming next. For example, it might output whether the subject is singular or plural, so that we know what form of a verb should be conjugated into. Alright, and you can see from the the equations as well. Again, we have a sigmoid function. Then that whatever output we get from there, we multiply it with tan ℏ to get the new output. Alright guys, so this is basically LSTMs in a nutshell. So in the first step, we decided what we need to forget. In the next step, we decided what are we going to add to our cell state, what new information we are going to add to our cell state, and we were taking an example of the gender throughout this whole process. Alright, and in the third step, what we do, we actually combined it to get the new cell state. Now in the fourth step, what we did, we finally got the output that we want. And how we did that? Just by passing ht minus 1 and xt through a sigmoid function, multiplying it with the tan ℏ the tan new cell state, and we get the new output. Fine guys, so this is what basically LSTM is guys. Now we'll look at a use case where we'll be using LSTM to predict the next word in a sentence. Alright, let me show you how we are going to do that. So this is what we are trying to do in our use case guys. We'll feed our LSTM with correct sequences from the text of 3 symbols. For example, had a general and a label that is council in this particular example. Eventually, our network will learn to predict the next symbol correctly. So obviously, we need to train it on something. Let us see what we are going to train it on. So we'll be training our LSTM to predict the next word using a sample short story that you can see over here. Alright, so it has basically 112 unique symbols. So even comma and full stop are considered as symbols. Alright, so this is what we are going to train it on. So technically we know that LSTMs can only understand real numbers. Alright, so what we need to do is we need to convert these unique symbols into a unique integer value based on the frequency of occurrence, and like that we'll create a dictionary. For example, we have had here that will have value 20, A will have value 6, general will have value 33. Alright, and then what happens, our LSTM will create a 112 element vector that will contain the probability of each of these words or each of these unique integer values. Alright, so since 0.6 has the highest probability in this particular vector, it will pick the index value of 0.6, then it will see what symbol is attached to that particular integer value. So 37 is attached to council. So this will be our prediction, which is absolutely correct, as a label is also council according to our training data. Alright, so this is what we are going to do in our use case. So guys, this is what we'll be doing in our today's use case. Now I'll quickly open my PyCharm and I'll show you how you can implement it using Python. We'll be using Tensorflow, which is a popular Python library for implementing deep neural networks or neural networks in general. Alright, so I'll quickly open my PyCharm now. So guys, this is my PyCharm, and over here I've already written the code in order to execute the use case that we have. So first we need to do is import the libraries. NumPy for arrays, TensorFlow, we know TensorFlow.contrib. From that we need to import RNN, then random collections and time. Alright, so this particular block of code is used to evaluate the time taken for the training. After that we have log_path, and this log_path is basically telling us the path where the graph will be stored. Alright, so there will be a graph that will be created, and then that graph will be launched. Then only our RNN model will be executed. Then that's how TensorFlow works, guys. So that graph will be created in this particular path. Alright, and we are using summary writer, so that will actually create the log file that will be used in order to display the graph using TensorBoard. Alright, so then we have defined a training_file, which will have our story on which we'll train our model on. Then what we need to do is read this file. So how are we going to do that? First is read line by line whatever content that we have in our file. Then we are going to strip it. That means we are going to remove the first and the last white space. Then again we are splitting it just to remove all the white spaces that are there. After that we're creating an array, and then we are reshaping it. Now during the reshape, if you notice, this -1 value tells us the compatibility. Alright, so when you're reshaping it, you need to make sure that we are providing in the correct parameters to reshape it. So you can convert a 3x2 matrix to a 2x3 matrix, right? So just to make sure that it is compatible enough, we add this -1 and it will be done automatically. Alright, then return content. After that, what we are doing, we are feeding in the training data that we have, training_file. We are feeding in our story and calling the function read_data. Then what we are doing, we are creating a dictionary. What is a dictionary? We all know key value pairs based on the frequency of occurrences of each symbol. Alright, so from here collections.counter words.most common. So most common words with their frequency of occurrence, there will be a dictionary created. And after that, we'll call this dict function, and this dict function will feed in word, and which is equal to length of dictionary. That means whatever the length of that particular dictionary is, how many times it is repeated. So we'll have the frequency as well as a symbol. That will be our key value pair, and we are reversing it as well. Then what we are doing, we are calling it build underscore data set, and we're feeding in our training data there. This is our vocabulary size, which is nothing but the length of your dictionary. And then we have defined various parameters such as learning rate, iterations or epochs. Then we have display step and underscore input. Now learning rate, we all know what it is. The steps in which our variables are updated. Training underscore iterations is nothing but your epochs, the total number of iterations. So we have given 50,000 iterations here. Then we have display underscore step, that is 1000, which is basically your batch size. So batch size is what? After every 1000 epochs, you'll see the output. All right. So it'll be processing it in batches of 1000 iterations. Then we have n underscore input as 3. Now the number of units in the RNN cell will keep it as 512. Then we need to define X and Y. So X will be our placeholder that will have the input values, and Y will have all the labels, all right, vocab size. So X is a placeholder where we'll be feeding in our input dictionary. Similarly, Y is also one more placeholder, and it'll have a shape of none, comma, vocab size. Vocab size we have defined earlier, as you can see, which is nothing but the length of your dictionary. Then we are defining weights as well as biases. After that, we have defined our model. All right, so this is how we are going to define it. We'll create a function RNN when we'll have X weights and biases. And after that, we are calling in RNN.multi-RNN cell function. And this is basically to create a 2-layer LSTM, and each layer has n underscore hidden units. After that, what we are doing, we are generating the predictions. But once we have generated the prediction, there are n underscore input outputs, but we only want the last output. All right, so for that, we have written this particular line. And then finally, we are making a prediction. We are calling this RNN function, feeding in X weights and biases. After that, we are calculating the loss and then we are optimizing it. For calculating the loss, we are using reduce underscore mean, softmax cross entropy, and this will give us basically the probability of each symbol, and then we are optimizing it using RMS prop optimizer. All right, and this gives actually a better accuracy than Adam optimizer, and that's the reason why we are using it. Then we are going to calculate the accuracy, and after that we are going to initialize the variables that we have used. As we have seen in TensorFlow that we need to initialize all the variables, unlike constants and placeholders in TensorFlow. All right, and once we are done with that, we are feeding in our values, then calculating the accuracy, how accurate it is, and then when optimization is done, we are calculating the elapsed time as well. So that will give us how much time it took in order to train our model. Then this is just to run the tensor board on local host 6006. And yeah, and this particular block of code is used in order to handle the exceptions. So exceptions can be like whatever word that we are putting in might not be there in our dictionary or might not be there in our training data. So those exceptions will be handled here, and if it is not there in our dictionary, then it will print word not in a dictionary. All right, so fine guys, let's input some values and we'll have some fun with this model. All right, so the first thing that I'm gonna feed in is had a general. So whenever I feed in these three values, had a general, there will be a story that will be generated by feeding back the predicted output as the next symbol in the inputs. All right. So when I feed in had a general, so it will predict the correct output as council. And this council will be fed back as a part of the new input, and our new input will be a general council. So it will be a general council. All right. So these three words will become our new input to predict the new output, which is 2. All right. And so on. So surprisingly, LSTM actually creates a story that, somehow makes sense. So let's just read it. Had a general council to consider what measures they could take to outwit their common enemy, the cat. By this means, we should always know when she was about and could easily. All right, so somehow it actually makes sense when you feed in that. So what will happen when you feed in these three inputs? It will predict the next word, that is council. After that, it will take council and it will feed back as an input along with a general. So a general council will be your next input to predict 2. Similarly, in the next iteration, it will take general council 2 and predict consider for us. And this will keep on repeating. So guys, this is it for today's session. Now let me just give you a quick summary of what all things we have discussed. So guys, we started by understanding why can't we use feed-forward networks for various problems. We understood few limitations of feed-forward networks. Then we saw how recurrent neural network solves those problems and what exactly it is. After that, we saw various issues with recurrent neural network as well, vanishing and exploding gradient. And both of these issues are due to long-term dependencies. Now, in order to solve those issues because of long-term dependencies, we use long short-term memory networks called LSTMs. So we understood what exactly LSTM is, and after that we even saw a use case of LSTM. So guys, this is it for today's session. Thank you and have a great day.